Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss about the module X-ray and extreme ultraviolet UV lithography from the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn in this module. First, we will discuss about the proximity X-ray lithography. Second, the synchrotron sources and X-ray mask will be discussed. Third, we will discuss about the extreme UV lithography and its exposure system. So students, let us start with a basic introduction about the module. Like the conventional optical lithography counterparts, extreme UV, EUV basically lithography and X-ray lithography utilizes photons to image the pattern devices. But unlike their conventional optical counterparts, they utilizes extremely short wavelength photons in the soft for UV lithography and hard X-ray for X-ray lithography regions of the electromagnetic spectrum. Of these two lithographies, X-ray lithography was the first to be successfully demonstrated to be useful in lithographic patterning. The resolution potential of both X-ray and EUV lithographies, given their short wavelengths, was the main motivation for their development. So the two main printing modes of these lithographies are in proximity mode for X-ray lithography and projection mode for soft X-ray lithography, which is also called as EUV lithography. In the following section, we will discuss the essential attributes of these two lithographies. Proximity X-ray lithography. The principle behind the X-ray lithography is to use the X-ray photons, which are having extremely short wavelengths in the range of 0.4 nanometer to 2 nanometers. So, this provides the advantage of preventing the diffraction effects associated with imaging features with sizes comparable to the exposure wavelengths of UV lithographies. However, in order to realize image forming lenses or mirrors, there are no known materials. Consequently, in X-ray lithography, the X-rays are passed directly through the mask, which is shown in this figure, which is brought to within a few microns of the wafer onto the wafer was proposed. The main advantage of X-ray lithography is that it provides the highest resolution by exploiting the shortest optical wavelength as compared to the other optical lithographies. So students, the minimum resolvable line width, which is represented by W in X-ray lithography, is given by W equal to root of lambda Z by alpha, where lambda is the X-ray exposure wavelength, Z is the gap between the X-ray mask and the wafer, and alpha is a parameter, that is a measure of the contributions from the resist. Typically, alpha ranges between 0.5 and 1.5. Furthermore, X-ray lithography offers critical dimension control, which is represented by CD, superior depth of focus, and the ability to project through surface contamination on wafers and mask. Also, due to the use of highly transparent resist films to X-rays, high aspect ratio pattern fabrication can be achieved. And so there is no restriction on the field size. Another advantage of X-ray lithography is the negligible unwanted scattering and reflection, which is due to the fact that the index of refraction is almost the same, which is close to unity, for all the materials in the X-ray spectral region. So students, this results in preventing the standing wave effects and other reflection-based problems, which are the main reason for limiting the resolution in other optical lithographies. But X-ray lithography comes with certain drawbacks, which includes the problems in fabricating 1x mask, the high cost of generating the X-rays at sufficient power, penumbral and diffraction blurs that limits the resolution in the case of point sources and overlay control. Students, let us now discuss about the synchrotron sources. Synchrotron storage rings produces X-rays 0.1 to 10 nanometer wavelength that have been used in X-ray lithography. In the synchrotron, electrons are accelerated up to 1 giga electron volt and maintained at that energy and circulated in an evacuated ring of a pipe which is surrounded by a strong magnetic field. As the orbiting electron in the storage ring changes direction in the magnetic field, they emit short wave dipole radiation. So under certain conditions, when the electron velocity approaches the velocity of the light, the radiation pattern changes from dipole type to a forward lobe, resulting in a strong continuous output of an almost parallel collimated beam of radiation with a wide range of wavelengths. One synchrotron storage ring can produce up to 20 beam lines that can be used in as many X-ray exposure tools. X-rays produced in the synchrotrons, they are ideally suited for proximity lithography because they are naturally collimated. So rays produced in synchrotrons do not cause nimbars, but they produces deep resist profiles with vertical sidewalls and astonishing aspect ratios. In addition, because of the extremely short wavelength of X-rays, diffraction effects caused by the mask substrate gap in proximity printing are minimized. Synchrotrons are not without drawbacks. So one of their major limitation is their extremely large size and the huge cost of ownership associated with them. Reliability is also a concern with these systems. So, for instance, a synchrotron can take a whole day or more to be brought up because they operate at 10 to the power minus 9 torr or higher vacuum. And the beam lifetime, it lasts only 24 hours. X-ray mask. Given that there are no materials that have excellent transparency to X-rays, X-ray mask comprised of very thin membranes which is of thickness 2 mm, typically made up of low atomic number materials on which the circuit patterns are placed in the form of high atomic number absorber materials. So, a high percentage of the X-ray passes through the low atomic number material but are absorbed or scattered by the high atomic number materials, thus generating a contrast for the pattern. So, students, typical materials which are used as X-ray mask membranes include silicon, boron nitride, silicon carbide, diamond, and silicon nitride. Typical materials which are used as X-ray mask absorbers includes gold, tungsten, tantalum, tantalum nitride, tantalum silicon nitride, and tantalum boron, with the last four materials being the most preferable because they are compatible with various etch and cleaning processes. Membrane materials must have a high Young's modulus, which is a characteristic that minimizes the mechanical distortion as well as makes the membrane damage resistant to prolonged exposure to X-rays. So here the use of thin membranes in X-ray mask presents many challenges. These challenges includes the film deformation because of stresses and susceptibility to vibration when stepped or scanned in an exposure tool. Now, mask can be deformed also, which is problematic in X-ray lithography, given that the imaging is 1:1 printing with no reduction. This necessitates very tight tolerances for X-ray mask relative to reduction printing systems. On the other hand, there are no lens distortions or feature size dependent pattern placement errors associated with X-ray lithography since there are no lenses involved. Projection soft X-ray lithography, which is also called as EUV lithography, was invented independently in the 1980s by research beams at NTT in Japan and at Bell Laboratories in the US, who were inspired by the availability of mirrors of reasonable efficiency at soft X-ray wavelengths, which is approximately from 4 to 40 nanometers. EUV lithography uses photons with 13.5 nanometer wavelength to expose wafers. It has higher resolution with suitable numerical aperture than longer wavelength photons used in conventional deep UV lithography. This results indicates that the resolution potential of the EUV system is approximately 5 times better than that of the Hyper NA immersion 193 nanometer lithography system, which is provided that the resist process used to print the EUV image can support the same K1 factor as the 193 nanometer lithographic process. Designing and fabricating such a resist that can enable such enhanced resolution is one of the main difficulty in implementing EUV lithography in manufacturing. In addition, producing an imaging system that can exploit the advantages of the short EUV wavelength is a very complex undertaking due to the fact that traditional materials which are used to fabricate the lenses and the mirrors do not have the required optical characteristics in the EUV range. So here the source chamber cannot be separated from the main chamber by a physical barrier because no known material has sufficient transparency to EUV photons. This places a significant challenge in being able to prevent debris in the form of particles, energetic ions, and neutrals generated by the hot plasma from getting into the main chamber where the illumination optics are housed. So, vacuum clamping cannot be used in EUV exposure tools because of the risk of generating particles. UV radiation cannot be transmitted through air, which makes it necessary to maintain the entire EUV exposure tool in a vacuum environment. So, outgassing of resist and components of the exposure tool inside the chamber therefore poses a significant contamination risk to the EUV optics. So students, furthermore, hydrocarbons and water vapors are cracked by the EUV radiation, contaminating the mirror surfaces via carbon deposition and oxidation of multi-layer coatings. So both carbon deposition and oxidation of the surfaces of EUV optical elements reduces the reflectivity of the mirrors and introduce wavefront aberrations to the projection optics. The overall effect decreases not only throughout of the exposure tool but also the imaging performance. Thus, it is necessary to minimize the hydrocarbons and water vapor content in the tool. There are no reasonably EUV transmissive refractive materials that can be used in the EUV optics. So instead of this, most naturally occurring materials reflect only a very small fraction of the incident EUV photons and tend to absorb most of them, so within a fraction of micron from their surface. Therefore, only precisely figured reflective optics, and the reflectivity should be of the order of 70%, comprising mirrors and reticles, can be used in the EUV tool. So even with reflective optics of the moderate reflectivity, there are still significant photons which loses through the exposure optics after the reflection from multiple mirror surfaces. That is only about 6% of the photons are incident on the reflective mirrors reaches the wafer plane. Also, because of the high EUV absorbivity of solid materials, including thin polymer films. There are no materials currently demonstrated with sufficient transparency that can be used as EUV pellicles. As a result, there are no pellicles for these masks, which represents significant defect control challenges in the lithography. Furthermore, EUV photons are sufficiently energetic to interact directly with bound electrons of the individual atoms of any given material. So, in this spectral range, there are a large number of atomic resonances which leads to strong absorption. So, students, the formula for the reflectivity R at normal incidence for an interface between vacuum and a given material is expressed as R equal to 1 minus n divided by 1 plus n to the power 2, where n is the refractive index of the material, 1 is the refractive index of vacuum. So, in general, R increases roughly as the fourth power of the wavelength in this regime. So, the influence of atomic resonances also increases significantly at extremely short wavelengths. It must be emphasized that the short attenuation length and normal incidence reflectivity of materials in the EUV range presents very difficult problems regarding fabrication of single surface mirrors or the lenses. EUV mask. This figure shows the cross section of a typical EUV mask, which comprises of an absorber layer, as you can see over here, which is typically of tantalum, tantalum nitride or chromium nitride, which is deposited on the top of the buffer layer, typically SiO2, separating it from MOSI multi-layer reflector. Now, students, note over here that the absorber material is titanium nitride. So, a capping layer, which is typically of silicon, is often deposited on the top of the MOSI stack to protect it from reflectivity, degradative carbon deposition, and oxidation reactions. So, fabrication of EUV mask involves the deposition of the buffer layer on the mask blank, followed by the deposition of the absorber layer, and finally we deposit the capping layer. So, by coating an appropriate resist over the capping layer and exposing with electron beam lithography and developing away the exposed areas of the resist, a relief image comprising of the open areas without resist and the resist covered absorber areas is printed on the mask blank. So, a pattern is transferred into the underlying layers through the open areas over the capping layer, absorber and the buffer layer, which is affected by the means of appropriate etching in a subtractive manner. So, here the resist protects the capping layer and the absorber buffer layer stack under it. Now, let us discuss about the EUV exposure system. The exposure system consists of the plasma source for generating the plasma that in return emits the EUV photons, the source collection optics comprising of the condenser and illumination optics, and the projection optics. A schematic of EUV exposure tool is shown in this figure. Now here, the EUV photons generated in the plasma source, they are collected by using specially designed optics. The collector optics directs the EUV photons from the plasma source to the intermediate focus, which is the entrance to the illumination optical system. So it is conventional to use the power level measured at the intermediate focus to specify the source power. The intermediate focus is also where a measure of how spread out the radiation is in area, and angle matching between the collector and the illuminator is implemented in order to ensure that all of the collected UV photons are accepted. So they are focused into the illuminator to avoid being wasted. Now the function of illumination system is to provide uniform UV irradiation of the reticle as well as the required degree of partial coherence for imaging. So the projection optics constitutes the last part of the exposure tool and is designed to produce a high resolution image of the reticle. It should also have very low distortion and aberration levels. So students, let us summarize what we have learned in this module. First, the proximity X-ray lithography was discussed. Second, a detailed description about synchrotron sources and X-ray mask were discussed in this module. Extreme UV lithography and its exposure system was also discussed. Thank you.